for the longest time, people just thought of like space and time as two different things, but then we know from Einstein that in fact we have to think about space and time as two parts of the same thing, which is space-time. Time is very, very different. So it occupies this strange space in our experiences as humans. Time is the universe's way of making sure that everything doesn't happen at once. But within that language is the word happen, which implies time. If gravity bends space, gravity also bends time. And I'm using air quotes here. Somebody should tie my hands down so I stop using air quotes. It is mathematically, theoretically possible to travel in time. Some of the conspiracy theories that I hear about CERN, where I work, right? They're like, you guys are causing time skips. If I took some books and I put them into a pile, look, entropy just decreased. And so like these kinds of religious creationists were like, checkmate atheists, look, I can make, so yeah.
Hey everyone, that's Renegade Science podcast and your host, Marie-Éline Puer. In this podcast, I meet scientists and entrepreneurs that are working on groundbreaking technologies that will eventually change our world. I talk to them about their work and areas of expertise and ask all the burning and stupid questions, the most important of which is, how do we build a great future powered by tack? Don't forget to subscribe to our YouTube channel and social media. My guest today is particle physicist at the Large Hadron Collider at CERN, data scientist, filmmaker, speaker, and an amazing storyteller, James Beacham. He hunts for dark matter, gravitons, quantum black holes, and dark photons as a member of the Atlas collaboration, one of the teams that discovered the Higgs Boson in 2012. James will blow your mind and you will fall in love with physics even if you always hated it. Let's go.
So, and now my quantum fields want to ask your quantum fields about time. So, time is a dimension, and although I can quite easily move myself in space, although I cannot go downstairs.
Tunnel through through the floor.
Yes, I cannot tunnel yet. We need to wait. But I cannot travel through time. So it seems that time flows only in one direction, forward. Why does time behave so differently compared to all the other dimensions?
This is another enormous fundamental question that no one really has the answer to, and not least of which is me. That's an extremely good question, and your observation is completely right, and it's one of the biggest, weirdest observations that we make, this notion that time, again, we know that for the longest time people just thought of like space and time as two different things, but then we know from Einstein that in fact we have to think about space and time as two parts of the same thing, which is space-time, which kind of makes sense, right? Also intuitively, like you said, there are dimensions or coordinates, right? If I want to make a date with someone, a coffee date, it's not enough for me to specify, the three, like in Manhattan, right? I can specify the east-west street, the north-south street, and then the floor that the cafe is on, maybe it's on the 30th floor or something like that, top of the Rockefeller. But that's not enough. I need one more coordinate, which is time. Otherwise, we'll be there, and we won't be there at the same time to have a conversation. So in that sense, it's just another coordinate, yeah. But as you pointed out, in another sense, it's completely unlike the spatial coordinates because I can't choose to traverse it, right? I have to go along with a kind of flow. It's like a river instead. So that means that time is very, very different. So it occupies this strange space in our experiences as humans, space. It occupies this strange place in our experience as humans and within the universe itself, within just existence and within physical reality. And the answer is that we don't really know why it does that. We have and the thing that's weird about it is that the question is such a fundamental one that, again, it goes back to this notion, is it even a well-posed question? Because, time may actually not just be a coordinate per se. I mean, it is because, we have to specify it if you want to make make some kind of specify when some event happened. But it's also so embedded within our existence and with our experience that it's impossible to separate it from existence itself. Because for example, all the stuff that we have talked about just now, when we talk about, describing what time is and how it occurs, the language that we use to describe that assumes the existence of time within it, which is not a good explanation, right? We want an explanation that gets outside of that language itself. So when, I say like, time is the universe's way of making sure that everything doesn't happen at once, which I don't actually know who first said that. I think it actually came from, I think it was first written in a science fiction novel in the 30s, but then it's been variously attributed to, I don't know, Susan Sontag or Carl Sagan over the years. But yeah, time is the universe's way of making sure that everything doesn't happen at once. But within that language is the word happen, which implies time. So there's any attempt to try to explain what time is inevitably falls into some kind of circular reasoning, unfortunately, because again, it's such an embedded part of our experience that we have no external way to think about anything that way, but the best kind of first principles way to at least start to get a grip on what time is something which I think you probably know, is this concept of entropy, right? And we talked about entropy a little bit earlier. It's this, this notion of disorder. It's kind of a measure of disorder, right? And people that are coming from other traditions might know entropy from, say, information theory. There's also an information theoretical notion, a communications theory notion of entropy. But basically, it's a measure of disorder, right? And we know from the laws of thermodynamics that entropy in closed systems over over long enough time scales, it only can go up. Yeah. Which means that it kind of seems sort of weird when you first read it. If you're a kind of clever person, you're like, wait, why are we even writing this down? Isn't that obvious? But it's true, because you think about it. It's like in smaller cases, in smaller scales, structure can form out from things that are less structured. So that, for example, we have structure around us. We have stars that formed. They didn't need to form. They weren't there at the beginning of the universe. Something had to happen. There had to be enough space in the universe for different forces to come together to allow this kind of a thing to congeal into structure. But if you go on long enough time scales, this order has to go toward disorder. Mm-hmm. And so we know that this is a case. We've never seen violations of the conservation, or sorry, the law of entropy, or the increased entropy on long scales on the appropriate systems to test it in. So this also must be the case on the scale of the universe. So therefore, people start to think, okay, perhaps time is not necessarily its own thing. It's simply just a consequence of the laws of thermodynamics, that it's the direction in which entropy increases. And it's a kind of in that sense, it's a sort of flow. Like I said, it's a river that we're always kind of going along with. And that's the best that we can do at the moment as a way to explain what time is. It's not so satisfying, because if you look at it in more detail, say like in general relativity and in black holes and things like this, we know that, from general relativity, like we talked about earlier, the presence of stuff within a certain volume of space warps the fabric of space itself, right? That's kind of makes a kind of sinkhole in space. But if that's the case, space and time, Einstein pointed out they're two parts of the same thing, space-time. So if gravity bends space, gravity also bends time. So if that's the case, it starts to mess with our explanations as to how time could be this one sort of thing, right? Because how does that change? And there's an entire field in and of itself, right? The logical extension of this stuff, I pack enough stuff into a fixed volume, eventually space will be bending and flowing so severely that it'll make a black hole. And this is a point where if you go past the edge of the black hole, space will be flowing inward faster than the speed of light, which means that nothing can ever possibly escape from it. But if it's also doing that to space, it has to do this in some form to time as well. And we know this is the case. If you watch the movie like Interstellar, right? They do a pretty good job with this. In places where you have more gravity, so to speak, or a larger gravitational field, time will pass for a person that's there compared to someone who's farther away from this gravitational field in a different way. So we know that time, in fact, has measurable differences. It can be bent by the presence of stuff. In fact, we even have to account for this even here on Earth, right? For your GPS system, right? The GPS system on your phone, in fact, has to be corrected for the redshift in the signal that happens due to the difference in gravity based on where you are on the surface of the Earth and the satellites that are the GPS satellites. The GPS satellites, there's a lot of satellites around the Earth, but GPS ones are the ones that are kind of very far away, the farthest ones away. And this distance, in fact, is such a large distance that the gravitational field is different there than it is here. Ooh. And if we did not correct for this difference, your GPS would be off by several kilometers. So we know for a fact that this is not just a made-up mathematical thing. It's a measurable thing for us too, not just in black holes. So all that being said, we arrive at this conclusion that time is this thing that is kind of tyrannical for you and I. We can't traverse it in any way that is measurable, and it also just seems to be pulling us along in one direction. And unfortunately, that's the best we can do at the moment for what time is.
I love the term for time, which is time is a measure of change, which is actually very adjacent to this idea of entropy, and the growing disorder in a system. Right. But if time, as we assume, goes in the same way for you and me, why a personal perception of time can be so different in one person?
Yeah, that's a good question. I think you'd probably have to ask a psychologist or a neuroscientist that rather than me, because it's true. I'm a physicist, and so I can't really speak to the the experience of time, human experience of time. But it's true. I mean, colloquially, we all know this, right? Like you're kind of suggesting our experience of time can in fact be very different based upon the context about this, the situation. Like if you spend a romantic weekend with your beloved, then time passes very quickly, right? But if you spend a weekend waiting for your medical test results, time passes very slowly, right? So we've all experienced this, and the pandemic was a perfect example of this, right? When there's all these kinds of shutdowns and lockdowns, spending a lot of time inside. And to me, I remember very clearly that I would notice, every few weeks, and I'm like, wait, did the pandemic start 10 years ago, or was that like yesterday? And I couldn't, based upon what I was focusing on, my experience of time was very malleable. And again, this part I don't really know. Like I said, we'd have to speak to, neuroscientists or psychologists to understand why the experience of time is so different.
Yeah, definitely. During the pandemic, many people were experiencing time travel, slowing down the time. But is it possible from physical perspective to travel, maybe not in the past, since we have no idea, but maybe in the future?
Yeah, so finally we're back in my realm that I can speak of. Even though I'm not actually a general relativist theorist, right? I mean, I'm an experimentalist, but all experimentalists are secretly theorists too, because but we also just want to take the extra mile to actually test the ideas. And so, with general relativity, what we know is that time travel is obviously amazing. And it would be great to be able to time travel, right? That would be fantastic. If everybody's seen the movies Back to the Future or whatever, and what was the weird one? Back to the Future 2 was the kind of dark one, right? Anyway, that's a good movie. Anyway, so it'd be fun to be able to do these kinds of things. But what we know for a fact from physics is that general relativity, I keep using these words, right? I think most people know what this is, but this is the best description that we have, the best theoretical mathematical description of how gravity works on large scales. And it's enormously successful. Basically, all of its predictions that we've been able to test so far have been like spot on. And even like Einstein keeps winning, right? I mean, even like in 2015, like 100 years after general relativity was formulated, we discovered gravitational waves, right? That was basically a prediction that long ago. So Einstein keeps winning. This was a wonderful set of insights. But the thing to keep in mind about general relativity is that it's not just one thing. It's a kind of framework to think about the universe. It's a way to think about and describe how gravity works, how these kinds of, how the presence of stuff, matter and energy density in space compels space and time to bend, and then how that curvature compels that stuff to move around. So it's not just one thing. And the reason I mention and belabor this point is that there's a lot of, when people say that general relativity predicts XYZ, that's not enough to say with that, because you have to specify what kind of general relativity you're talking about. And the reason I say this is because it's a set of mathematical equations, and I can solve them in certain ways for certain kinds of physical systems. But when I do that, I have to specify exactly how I'm doing the solving. The reason this is necessary, and the reason I'm belaboring this point, is exactly because of that concept that space is bending and time is bending too. Space can bend and flow. But if that's the case, the clever amongst the listeners here would have thought to themselves, well, wait a minute, if space bends and stretches, then how can I measure anything? That's a really good question, right? Yeah, it's a good question. So if I have a meter stick, right? And I'm like, oh, I'm going to measure a meter. But then if I say, it's like, I'm going to measure how much space is expanding around me, right? And so I'm going to measure, and then I see space going in one direction and the other direction. I'm like, aha, I measured it. But wait a minute, my meter stick is in the same space. The space is also must be bending my meter stick too and stretching my meter stick, right? It's absolutely true. It's a completely valid question. So a version of this is what we refer to as the measurement problem and the metric problem. The way you get around this is that within general relativity, it's fascinating because it's not just, a lot of people here might know about some mathematics where you talk about like scalar quantities, numbers, vector quantities, right? Which is not just a number, but it's also direction, right? If I have a vector, it means that, I can't just say 10, that's not a vector. Instead, I have to say 10 this direction, specifying the wall or something like that. But then there's another quantity that's sort of above that, which is called a tensor. Mm-hmm. And the tensor is not just, if a scalar is like, what's happening, and then a vector is what's happening in that direction. A tensor is something where it's like, what's happening in that direction if I think about the other directions being kind of held in a certain way. So it means it's a much more complex mathematical object. And if that's the case, you then have to, once we understand these kind of tensor mathematics, and especially you can use this kind of tensor mathematics to describe more complex three-dimensional systems in general relativity that describe how space itself moves. So if that's the case, then we have to specify our so-called coordinate system in a vector quantity. I have, like fixed coordinates. Again, I'm getting a little bit mathematical here, but those people that know will know what I'm talking about. If I have like a vector space, right? If you've done some linear algebra or something like that, if I have a vector space, I have, say, a three-dimensional space, I have to specify a unit coordinate system, right? Mm-hmm. But these coordinate vectors are they're not going to move, they're not going to change, they're fixed. And this one goes in that direction, x, 1x, 1y, and 1z. And if I have these three coordinate vectors, unit vectors, I can describe all of the phenomena in my system at all. In a tensor system, in a general relativistic system, I can have coordinate vectors that in fact bend themselves, and they in fact change based upon where they are in my system. So I think it's beyond the discussion here, but that starts to get at how we can start to specify in a mathematical sense this measurement issue and this. The
travel in time.
Well, we're getting to the time travel part. The reason I mention all of this, and I promise I have a point here, is that once you specify that, it's a much more complex idea to specify how things happen in general relativity. So anytime I do anything in general relativity, I have to specify what my metric is. Mm. And I'm using air quotes here. Somebody should tie my hands down so I stop using air quotes. And so I have to specify what my metric is, meaning how am I measuring anything? So all of that is to say that there are certain ways that you basically have to make some assumptions about general relativity first, before then you can start making doing equations. So if I make certain equation, make a very simple assumption, a kind of simple metric, blah, 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 I can then describe everything around us, the sun, the earth, the moon, our solar system, the galaxy, no problem. If I want to then go to extreme conditions, I have to specify other things. So if I want to describe a black hole, I have to specify certain ways to think about general relativity before I can then say anything. I can make any conclusions, mathematical conclusions and predictions. This is where black holes come from. And then so then people immediately, even to this day, but immediately they realized this was the case, and theorists love to shake it, like, ooh, what can I do with this? So they started taking it to its extremes. And under certain assumptions, you can have solutions of the equations of general relativity that allow so-called closed time-like curves. All of that is to say that yes, under certain, that's the extremely long version of saying that it is mathematically, theoretically possible to travel in time. However, number one, we've never observed any time travel. I guess that's true. We always need to specify that time travel we know is possible. It's this that you and I are doing it right now. We're moving forward in time at a rate of 1 second per second. Okay, that's kind of the trivial case, right? That's this river we were talking about, this river of time. But it seems that it is possible, theoretically possible, that we could travel in time. And it is in principle possible to do forward time travel or backward time travel as well. However, there are some, if you look more closely at these solutions that allow for backwards time travel, they have some bigger problems, and it's entirely probable that it's not possible to go backward in time.
Yeah, the paradoxes of different.
Yeah, well, there's those too. I mean, there's the logical paradoxes too, right? This notion that this notion of going back in time to kill your grandfather, things like that. The grandfather paradox, but also the things like we've never observed backward time travel, right? I mean, several years ago, what was it? A bunch of people had at a party. They were like, okay, well, maybe people in the future have just been shy and they didn't know what to do. So we're going to have a party. We'll say, yes, we're going to, I forget where they held it. It's like at MIT or something. We're going to have a big party. Welcome future time travelers. We welcome you for this moment. And they said they were going to have it on a certain day. And if anybody showed up, then that would be a good time for them to show up. And they didn't. So they figured that this would rule out the idea of backward time travel. I don't know. I have my own ideas about this. I think that it's similar to the idea that a lot of people wonder why, it seems logically weird that we're the only civilization in the universe, right? And some people think that maybe this is because alien civilizations, if they've mastered interstellar space travel and they've observed us, they probably have concluded that we're not very smart and they don't want to have anything to do with us. Because for one simple example, we have known the science behind anthropogenic global warming for decades, if not 100 years, and we continue to do it. So they're probably like, whoa, we don't want to talk to those people, very stupid. It also might be the case with time travel too. Like if you're in the future and would you really want to come back to this time right now? Like this is a really bad time to be alive when, the United States of America literally elected a fascist for president. This is probably not the first the first time that I would come back to if I were living in some kind of future utopia. But it's, in principle, it's possible to do backward time travel, except it seems very unlikely. There's also some things about the stability of these kinds of closed time-like curves, but we don't want to get into the weeds of general relativity here, but it seems that forward time travel in principle could be possible. And there, of course, have been some very speculative ideas as to how this happened, different types of, warp drives and Alcubierre drives and things like this. But forward time travel is entirely possible. Backward time travel, theoretically possible, but probably less likely.
How about time loops?
Time loops, like what? What do you mean?
I mean, these situations when you live through the same period of time again and again and again, or like a full city is locked in, 3 days.
Like a Groundhog Day type thing.
Yeah.
I don't know. That's beyond me. I think we'd have to talk to science fiction authors to get a better sense of that. I don't know. I get the sense that, time loops. Oh boy, this when we start talking about time loops, it makes me think a little bit too much about some of the conspiracy theories that I hear about CERN, where I work. Right? They're like, you guys are causing time skips, and you're causing the Mandela effect. Anyway, so this starts to remind me of these kinds of questions, which I don't really even know what they mean. Right? I don't even know what it would mean to have a human get into a physical time loop. I don't know, because again, if you have your own memory and then you remember being in the time loop yesterday and then it happens again, how does that work? Again, physically, that's going to be very difficult to realize.
So with forward time travel, it's a bit simpler than with a time loop.
Yeah, well, time loop would be hard to pull off. I guess with sufficiently advanced technology, maybe future civilizations would be able to imprison people in time loops. Like you could imagine that being a very sophisticated carceral system. If somebody is an evil person and they do bad things against the laws, instead of putting them in a spatial prison, you put them in a time prison instead.
But that would be very simple, I think. You just use like VR, and put a person in a constant loop.
Yeah, no, you could simulate the time loop for sure. But if you wanted to really do it right, a physical time loop where they knew that they were living the same day over and over. Oof, sounds terrible. Sounds terrible.
Yeah.
As an anti-prison person, I'm not advocating for this, by the way. Just to be careful.
Okay, and let's continue on a more positive note with anti-prison topic, escaping the aging. So we talked about time and the entropy and the decay of everything. So what about, is it physically possible to reverse aging or to stop it? Because it's against all the laws of physics, no? Well, from a perspective of a physicist.
As a physicist, yeah. Well, again, I think that one is probably outside of my expertise to be able to say for sure. The only thing that we know from a physics perspective is that everything that has structure in the universe eventually will decay and disintegrate, except for a few things. Like I said, photons, right? We're bathed in photons right now. Photons can't decay into anything because they, if I think of a photon as, as you know from quantum mechanics and light, there's this sort of wave particle duality, right? And it also happens for matter things too, but for photons especially. Photons, you can think of as a little chunk of light moving through space, but it has zero volume and it has zero mass. So it's just this it's radiation, pure radiation moving through space. And if that's the case, it can't go anywhere. It can't disintegrate into anything. It just will continue to exist forever. Yeah. And so, and if you have an expanding universe, like we talked about earlier, in the very far, far future, 10 to the power 1,000 years, the universe will be so large and so expanding everywhere in all directions that the light will just be hanging out and just sit there forever. It can't stay still. You can't pause light. But it will go at the light speed in whatever its little local patch of space it is that feels like it's going at light speed, and it will just do this forever. But it can't disintegrate. It can't turn into anything. This is other things. They have to turn into other things eventually. So for example, like I said, protons. We think that eventually they must sort of fall apart and decay. We also think that, we know that neutrons do this too. We know that, even electrons, in principle, they could be absorbed by things before. And so it gets a little bit weird, so that the fundamental particles themselves being quantum fluctuations, if you get to such a very, very far future state that this maximum entropy, then it's not even really possible, except, occasionally in this kind of fluctuation way, they can't really turn, they're kind of stuck. So we're left with a very small number of things that can't disintegrate. Everything else has to disintegrate. So from a physics perspective, yeah, it kind of makes sense. But, again, biology is not strictly physics. We know that within, I know maybe that's funny for a physicist to say, because deep down inside everything is physics. Let's be honest. It's true.
That's logical.
But we also know that the reason these other sciences exist is because there are principles and laws and rules that also occur on other kinds of systems that are accurate to describe those systems, that are not needed for, you don't need physics to describe. Like, it makes no sense for me to describe the birth, the conception, birth, and death of a human from trying to model every single one of the particles that is in this person's body, right? It makes no sense, because that's not the level at which the changes occur. The noticeable changes. Instead, the changes occur at molecular level and also at the macroscopic level, right, where things come together, and genetic level. And from that perspective, yeah, again, I can look at a human body and I can, as a physicist, I can say, yep, basically this is just a bunch of fundamental particles. And these molecules themselves have substructure. And we know that eventually all molecules are going to break apart, very, very far enough time scales. So it makes sense that, even on smaller time scales, these molecules just kind of decay and they'll degrade and different things. Again, but this is not true. We know that we can track, I think you know better than I do, these people that track try to look for sort of biomarkers of
Yeah.
aging. It's like, how does aging occur? Why does aging occur? Why is it necessary? But again, from a physics perspective, we know that every 7 years or so, your body has completely different particles, right? Different cells, right? So you're basically a new person, but you're not, because the memory of who you are is embedded within that structure that's not just the individual molecules themselves, and individual. So that's fascinating. So again, this is beyond me. I'm not a biologist. I'm not a geneticist, and you probably have to ask them why these kinds of things happen.
Yeah, they also don't know. That's why I'm asking you.
Yeah.
But probably that's because every system just grows up in entropy and at some point dies.
Yeah, but even on the scale of entropy, again, we know that this notion of the arrow of time and being very intimately connected to the direction in which entropy increases. That again is on the level of the entire universe, right? We know that on smaller scales, entropy can decrease, right? What's a good? I don't know what a good example is. Like if I took some books and I put them into a pile. Look, entropy just decreased, and so like these kinds of religious creationists were like, checkmate, atheists. Look, I can make so yeah. Anyway. So we know that within systems that are not fully closed, because that wasn't a closed system, that was me from outside making things happen, that entropy can increase. And keep in mind, on the scale of the universe, even right now, forget about 10 to the power 1,000 years, 13.8 billion years, the amount of time that humans have existed is basically nothing. It's basically nothing. Like even the current age of the universe doesn't even acknowledge that we're here. So this is more than enough time for other sorts of principles and other kinds of rules of biology to come together and operate the way they do, and then eventually probably in the next few decades humans will be incinerated due to anthropogenic global warming. So that will be a academic question at that point. But these kinds of structures on the biological scale, they do have their own time scales, and it's totally possible that you don't have to appeal to entropy increases on like a human time scale, because it doesn't have to. And so from a physics perspective, the time scale of human evolution has been tiny, tiny, tiny. And in principle, there's no reason why
it can be a little bit.
Yeah. There's no reason why, from a physics perspective, this is a tiny, tiny window of time, right? There's no reason why I couldn't, if I had some magic device, just sort of like keep replacing the exact same, cells and molecules that I have with new ones, and just replenishing them, and just have
changing for new ones every 7 years.
They are.
Yeah.
And so why couldn't I do this indefinitely, or even for a bit longer than 100 years, 80, 100 years? So again, this is outside of my expertise, so I'm just sort of jabbering here. But from a physics perspective, there's no reason why that shouldn't be able to be increased or extended quite a bit.
We have questions. Marcel is sitting there with a notebook, and
Please.
We have a question.
From
We have a
great.
question from the audience. Yeah. What did the Big Bang Theory do for your field? I know that Marcel was very interested in knowing that.
Oh, you mean the TV show?
Yeah, the TV
Oh, I
series.
thought you were talking about Big Bang itself.
No.
Yeah, so it's strange. Just because of the universal presence of that show, as a physicist, it's inescapable. And here you want to know the truth? I have never seen a single episode of the Big Bang Theory show. I've of course I've seen it, like people watching it on airplanes, and I've happened to see this kind of thing. But I'm not anti the show. The parts that I've watched, I'm like, haha, that's very funny. But it's not my thing, right? It's like, so I don't gravitate toward it. No, I don't gravitate toward it, but I'm not anti that show. But the truth is that I don't really know that much about the show. I know the kind of stereotypes about the characters and things. So the one thing that it has changed about my field is that it makes every person that I come into that is a fan of the show assume that I'm a fan of the show too.
Or ask you questions about the show.
Which, again, I don't say this is a bad thing. It's completely fine. And one thing that it has done, and I think that within scientists that have watched it, it gets a little bit of a bad reputation, honestly, because it's very silly and it kind of, denigrates. It's very, it trucks in broad stereotypes about scientists, and so I think that some people, they're a little bit of grumbling about how it's like, oh, well, not all scientists are like that. I don't know. In my experience, a lot of physicists are like that. So let's be honest, like it's totally true. Not everybody, but yeah, physics attracts a certain type of person who's very particular and very kind of, hardcore about certain things. Oof. If you wanted the truth about my field, about particle physics, experimental particle physics, I don't know if any of my colleagues will be watching. There's actually very little creative thinking that goes on in my field. I'm sorry to say that, but it's totally true. Like a lot of physicists, they speak not in like questions. Theoretical physicists speak in questions and things, but like the experimentalists speak in like declarative sentences. It's like, this is the way it is. This is the way it is. It's actually super weird. Anyway, so I'm trying not to, this is no shade toward my field, maybe a little bit of shade, but it's super strange because people think about like physicists are they must be such creative thinkers and like imaginative out of the box. This is not really the case. Anyway, so I know that The Big Bang Theory is a very popular show. I've never really watched that much of it myself, so I can't speak, but it has affected the field in that way. Another thing that I think it has done overall, though, is that I'm sure that for a non-zero, probably sizable number of students who came into it, or came into contact with it, something in one of those episodes probably sparked some curiosity and guaranteed that it led them on. For example, if the first time that a person ever heard of the Large Hadron Collider was through a goofy episode of Big Bang Theory, and then they actually looked it up and they're like, oh, that's interesting. And then that moment where they switched over from just casual, TV watcher to like, oh, what is that? Wait, proton collision? What does that mean? And then they turned into a scientist. Then, boy, howdy, I can, I'm happy to accept the help of TV shows like that. So I'm not sure it hasn't changed the science, to be honest. There's not sorry, this is nothing bad against, Bill Peretti and the other guys that made that show. But there's not been a single discovery that's been made because somebody watched an episode of Big Bang Theory. So it hasn't really changed science. But maybe it's helped get some scientists in the field. So.
Well, still not bad. Talking about collider, where were you when the Higgs boson was detected? Did you pop some champagne? How do you experimental physicists celebrate discoveries?
Yes, good question. So in fact, I did help with the discovery of the Higgs boson because I am a member of the ATLAS collaboration, one of the two collaborations that discovered the Higgs boson, announced the discovery in 2012, and I was a member of that team. I was in graduate school at the time, and I had been a member of ATLAS for about a year, and the Higgs discovery wasn't my main project, but everybody was helping because, the discovery itself didn't just happen like overnight. It's not like you didn't just, when we collide protons at the LHC, we don't just collide two protons and turn off the machine and say, what happened? We do it 40 million times a second. And we do this for weeks and months and years because what we're looking for are tiny, 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 improbable, like we were talking about earlier, the kind of probabilistic nature of quantum mechanics. If something is allowed, it has to happen. It might not happen very frequently, but it has to happen eventually. So we do this 40 million times a second for weeks and months and years, so that if there is a real effect, it might not be just a little fluctuation, but it'll turn into a nice kind of peak, a sort of anomaly, a deviation that is statistically significant. So we started to see things happening, in our data. We started taking data, I guess that was 2009 or something like that, 2010. And then we started to pay attention to the data, and then we started to see something, a little bit of a kind of bump. It's like, oh, this is a bump. Is this real? And so everybody's like, okay, all hands on deck, let's help. And so I was a graduate student doing my PhD in New York at New York University. I was based in New York at that time because CERN is an international collaboration. It's something like 4,000 people work on the ATLAS experiment, and they don't all live in Geneva like I do. And so, I was based in New York at the time, and we started to see things happening. And in fact, the New York team, the NYU team, was one of the key teams that was working on not just the analysis of the data, but the final statistical statements made about the data too. So I was like right on the front lines of seeing this little fluctuation turn into an actual statistically significant bump. I mean, I think one of the students that was one of the graduate student grunts that was working on the statistical analysis, turning the crank on the things. I think he might have been the first person in history to see the the bump go over the 5 sigma statistical significance level from NYU. So that was cool. Yeah. But then, of course, you have to go through the whole collaboration and make sure that it's approved and everybody understands it and agrees with it. So then on July 4th, 2012 was when we made the announcement. And we knew what we saw. The interesting part for those of us that worked on Atlas is that we did not know what the people in CMS had seen. Of course, there's rumors. And by CMS, I mean this is the other kind of sister experiment to the Atlas experiment. There are 2 opposite ends of the Large Hadron Collider ring, this 27-kilometer circular tunnel. Not because we fight, but just because they were designed on purpose that way to be intellectually independent. So they can corroborate each other's findings independently, right? So if I work on Atlas, I cannot work on CMS and vice versa. So we knew what we saw, and of course, people talk and try to, there's rumors, but of course we try to, we're scientists. We want to make sure that we trust our result. That's the whole point. So when we made this announcement, we had this seminar. We didn't know what the other experiment was going to say, and so we made our little presentation where it's like, yeah, we see an actual bump. It's a real thing. And then CMS is like, actually, we see all the same bumps in all the same places. Ding! And so we knew that we had something there. So at that point, yeah, I was on the 6th floor of the physics department in Greenwich Village in NYU on July 4th, 2012. And yeah, we had some champagne and we celebrated. And yeah, so it was good.
Yeah, that sounds like a party.
It was. If physicists like to party, it's true.
So also Marcel asks, what are the best movies to watch to understand your field of work?
Oh boy. As far as I'm aware, there are no films about my specific part of particle physics, which is collider physics, big, enormous colliders. I don't think there's a single film about that. And if there is one, then it's bad enough that no one talks about it anymore. So if you want to talk about physics in general, oh boy. I don't know. That to be said, there are some documentaries that have been made, and I'm not tooting my own horn, but I've been in several TV shows and documentaries about my field, and those are, of course, the best ones that everyone should watch. Yeah, you should definitely watch the best. Sorry, I take it back. The best film to watch about my field is a documentary film called Chasing Einstein from 2019. So look up Chasing Einstein right now. It's the best film, by far, the best film that just happens to be me in it. It was really cool. Some documentary filmmakers, they followed me and a few other people around for several years. It was about dark matter. They were talking. We were trying to, he's trying to dig into, the kind of mindset of people who devote their lives to these kinds of things, where we don't even know if it exists, but we're trying to, rule out all the possible places it could be. So that's by far the best film to watch about my field. Feature films, I don't think there's any. I don't think there have been any, but there are some, of course, really good feature films about physics, and I think probably the best ones are the ones that everybody knows. Interstellar is really nice. It's a good film because Nolan's a good filmmaker, right? He's a very he's kind of a scientist for film as well, because he's very particular about what gets into the film and how it gets put together. He's kind of an engineer, physicist, filmmaker. At least in mindset. And of course, they did use real physicists. They employed real physicists to help them to make the visualizations of the black holes and the wormholes and things like that. And so most of it is, some of it is scientifically accurate. Of course, at some point it's a film and they have to make extrapolations for the sake of poetry. And as a filmmaker myself, I totally understand that. I support that. But here's the thing, the deviation, the part where the science, reality starts to deviate from the film. Okay, like I said, we don't actually know what happens inside of a black hole. But one of the things that we know is probably not what happens inside a black hole is that you probably don't go back in time behind your daughter's bookshelf. It probably does not happen. But hey, yeah, who knows?
Oh no, I hope so much.
Yeah. Another one that's really good is, I'm not really a big Zemeckis fan, but Contact is a pretty good film, just because, again, it's mostly based upon real science in terms of these things until it starts to go into extrapolation places. I don't know. I personally, the thing is that I don't think there's any really good film to understand fully what it means to be a scientist that goes into physics or astrophysics per se. And so I tend to like some of the sillier films that take themselves way too seriously and start to be very bad in their physics too. There's a great movie from the 1980s or maybe the 70s. It's a Disney movie called The Black Hole. And this was a crazy, crazy film, extremely influential on me as a child, because I watched it as a child and was like, what is going on? And as an adult, you watch, you're like, this is so bad. And it's like, because it's silly and the characters are dumb, and there's a bunch of stuff in it that obviously just trying to like ride on the popularity of, you know, Star Wars and things like that, with silly robots and stuff. But then there's like this fireball that's coming toward them. They're running on this thing in a spaceship. That was very influential on me as a child. But then you see this black hole, it's like this swirling thing, and physically that can't happen. So as a physicist, you're like, this is impossible. But as a little kid, you're like, wow. So
I didn't ask you, how did you become a physicist? By now I know.
yes, blame it on the Disney film, The Black Hole. No, it's not. That's not the reason, but there are a lot of things that were influential on a lot of us who end up being scientists, me for sure. And that was one of them. Other films, I don't know. I don't really have a film watching list that people need to watch to understand physics. I think they need to go and do PhDs in physics instead to really understand.
Perfect.
No, actually, I don't say that. It's not for everybody. PhDs are for obsessed people. But if you're this kind of person who's just interested in this kind of a thing, even to the point just shy of obsession, you don't need to take 6 years of quantum field theory calculations to get a sense as to why it's interesting. And I think that's one of my goals. Not even goal. That's one of my that's one of the things that I have been selected by the cosmos to do, is to engage with people in different ways so that they get a sense as to why this is interesting. Because you can read things in an article, or you can read people, you can hear people in the Big Bang Theory TV show, speak excitedly about loop quantum gravity or something like that. But then to get a sense as to really, really do that study itself, you have to go down the rabbit hole of a PhD or something. But to get a sense as to why it's interesting and why it actually matters to your life, that's its own task, and I find that fun.
Yeah, this is how to get new acolytes.
Yes, keep the wheel of human curiosity going.
Absolutely, and I think this is a nice moment, to wrap it up. Thank you so much. It was such an insightful and fun discussion.
It was my pleasure. Thanks for having me.
Oui.
Bravo, bravo.